Hi, welcome back. In this chemistry lesson, what we are going to be doing is expanding more on the structure of the atom. So the nucleus of the atom contains the protons and the neutrons, and the nucleus of the atom really isn't this very controversial thing. It's literally, protons are solid, very tiny little subatomic particles with a positive charge. Neutrons are equally tiny, neutrally charged subatomic particles, and they combine together and form this solid, dense nucleus that has a definite dimension, a certain, width, diameter, and a certain mass. But the electrons, we know they're negatively charged. We know what their mass is. It's this incredibly tiny number, which I don't have memorized off the top of my head. But electrons have extremely bizarre behavior. In fact, the whole idea of quantum mechanics arose from studying both photons and electrons, which both behave in just this unbelievably strange way. And so one of the things we have to try to do today is talk about quantum mechanics. I don't quite feel qualified to do it, but I've read and learned everything I can to try to help it make a little bit of sense to you, at least. And this is important going forward because as we study chemistry, and we study how matter interacts, how compounds and molecules are formed, well, when two atoms chemically bond, it's only their electrons that have any kind of real interaction, because the nucleus is isolated and it's extremely far away from those electrons on the atomic scale. At least it's extremely far away. Ernst Rutherford, he was the one who discovered the nucleus, basically. He didn't discover the proton, but his atomic model, it did a very good job of finally explaining, yes, there's a nucleus with positive subatomic particles in it, and then the neutron is probably in there too, and then the electron is separate from the nucleus. Before Rutherford's model, we had the plum pudding model, you'll remember, where we know atoms are electrically neutral, but it was thought that the electrons and the protons were mixed together into some sort of matrix that just neutralized itself. Well, Rutherford proved with his gold foil experiment that no, the positive region of the atom is in a separate location from the negative region. Kind of like how the planets orbit the sun, but they're separate from it. They're both part of the solar system, but they're not connected together in any way. But Rutherford's model didn't tell the entire story. It couldn't explain why atoms behave the way they do. It really said nothing about why do elements form compounds in the ratios they do. Why is it H2O? Why not H3O or just HO, for example? It didn't tell us how elements actually bond together at all. This is something we will not be getting to probably, but this has to do with what's called the photoelectric effect. Albert Einstein won a Nobel Prize in it. But metals, as you heat them up, glow different temperatures. And it has to do with electrons rising and falling in these different energy levels. We'll talk a little bit about them, but not specifically this last example. So Rutherford, his model basically was what's on the left. So all we know is that the electrons, the negative part of the atom, and the protons, the positive part of the atom in the nucleus, are separate from each other. But we had no idea how to organize it. Do the electrons all share the exact same space, or are they compartmentalized in different areas around? We had absolutely no idea. Now on the right, this is called like the planetary model. And Niels Bohr helped develop it. We'll talk about him very shortly. But we call this like the planetary model, where we show that the electrons are in very specific places, and only a certain number of electrons can fit in each of these little locations. Now, that's also not 100% accurate, but for the purposes of trying to understand atoms, things we can't even see individually, it works pretty darn well. So, here's Niels Bohr. He was from Denmark, and he was actually a student of Rutherford's, and Rutherford was a student of J.J. Thomson. So the guy with the plum pudding model, his idea got overturned by Rutherford, and then Rutherford's idea was then improved by Niels Bohr. So there's kind of a passing of the torch there. But anyways, he made further revisions and updated us on some things about how atoms emit light. So Bohr did pretty much most of his work on hydrogen. It's the simplest element. It only has one proton, and most hydrogen in the universe doesn't even have a neutron, actually. So its atomic mass, for the most part, is usually just 1. There are isotopes of hydrogen, but usually, most common, 1 proton and 1 electron. The simplest possible particle of matter that you can, well, the simplest possible element that you can study. So Bohr got like we saw in the picture before, he got this basically right, where he said an electron can only be in one specific circular path, we call it an orbit, or you can call it an orbit, around the nucleus. So they go around the nucleus in a fixed, or there's a fixed region where they are. They don't go out here, over there, blah, 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 blah. And that's kind of like, planet Earth. It orbits around the sun, but in a very predictable path. We don't fly out way to where Jupiter is some years and then come all the way back into our spot in the solar system. We sort of stay in place. Now these orbits, there's a fixed amount of energy associated with that orbit. And so as an electron sits inside of one of those orbits, it occupies it. That electron contains a certain amount of energy. And so these different places where you find electrons around the nucleus, they're called energy levels, and there are many of them. And we use this term quantum. Quantum is just the amount of energy it takes to move an electron either up one energy level or down to the previous energy level. So this is, in simple terms, kind of how the energy levels work. There are only 4 of them shown here. There are way more than 4. But the first energy level, there are only 2 electrons that can occupy that energy level. When you go to the next energy level, there are a total of 8 electrons that can occupy that space. Once you get an element that has more than 10 electrons, 11 for example, then that 11th electron has to go to the 3rd energy level because the first 2 are totally filled up, and then an additional 18 can fit in there. So the element with the atomic number 29, 18 plus 10 is 28. So once you get to the 29th element, which off the top of my head I don't know what that is, its electron has to go to that 4th energy level because the first 3 are all occupied. And here's the picture again from before, just to show. In this case, this is a nitrogen atom. So the first 2 electrons go in that first energy level, and then the next 5 go in the next energy level. Here's just another way of showing the same thing. So what's important about this, as in terms of a development or an evolution of our understanding of atoms, is the electrons have to be in very specific places. One electron is not really free to, like the distance, I guess I should say, that an electron will be from the nucleus is fixed, and it's in this 3-dimensional spherical kind of, in some cases, shape. It's not allowed to just go way out here and then come back unless you add energy to it, like heat, for example. And that's our equation. We're not really going to worry about this, but there's the equation for determining how much energy is lost or gained by going up or down one energy level. Don't really worry too much about it. We're just taking a glance at it here. So, if you add energy, and heat is the easiest way to think about it, if you add energy to an atom, you will force some of its electrons to jump up to higher energy levels because they have to accommodate for that extra energy. But electrons always want to be in the lowest possible energy state. So as soon as you stop dumping heat into them, the electrons will naturally jump down. So they have to give up that energy they absorbed to do that. And as a matter of fact, the electrons emit a particle of light, a photon, when they do this. So this is what Bohr basically figured out. And his model worked really well for hydrogen, but it failed to make the necessary predictions to accurately describe anything else, any other heavier elements. And the problem was, it was easy for hydrogen because there was only one electron to worry about, but for other elements that have more than one electron, it turns out what electrons are actually doing is extremely weird. And so we had to develop a quantum mechanical model in order for it to make any sense. Not that quantum mechanics really does make any sense, but it does actually make huge numbers of predictions, totally accurate predictions. Quantum mechanics is the single most accurate scientific theory we've ever come up with, but we don't understand how it works. And you might see what I mean by that, if I can actually explain this well. So I said this, the Rutherford and Bohr models, they describe the atom and the electrons particularly like planets in a solar system. But while that does work for the nucleus definitely has a certain dimension and it definitely stays in put, kind of like the sun does. Electrons are, the term is spooky that's been used for them. Electrons can do unbelievably strange things. Erwin Schrödinger, who's from Austria, he developed the quantum mechanical model. And this model tells us that, well, it tells us what amount of energy the electrons have, and it'll tell you where they can be, but you can't ever know precisely where an electron is. Or if you do measure an electron and you find out it is exactly right here, you cannot then know where it will be in the future. That's what makes quantum mechanics completely different from classical mechanics. So we can't know where an electron is without looking. Now, for planets, I have a model that I'll show you later, but, we have software and programs and you can do the math, and I can know exactly where planet Earth will be in terms of like its orbit around the sun. I can know exactly where Earth will be in 10 days, in 10 years, in a million years. It is possible to know exactly where Earth will be because we just know it follows the rules of classical mechanics. But electrons, it does not work that way. You cannot predict where an electron will ever be, even if you do measure and sort of see the electron. You can only know, statistically speaking, where it might be, which is an infinite number of locations. It turns out that electrons they have these paths, they're called orbitals, where they fit around the nucleus. But we have to assume, or we have to conclude really, that the electron is in all parts of that orbital at all times. It's in multiple places at once. In the act of looking, trying to find out where the electron is, it transforms from being in what we call like a probability state or a wave function. There are many ways of explaining it. But it goes from being everywhere all at once to exactly right here. It literally transforms right before your eyes. I will try to show you how we know that in a second. But really quick, on the right, so there's like the simple hydrogen atom. There's the nucleus, and then there's the electron. So we could imagine that we could watch that electron orbit around the nucleus, but you can't do that. You cannot watch an electron move around. It just simply isn't possible. So instead, we assume that the electron is like what you see on the left, where it's this sort of three-dimensional sphere, and the electron is in all of those places all at once, and it is equally likely, therefore, to be in all of those locations at once. Now, when you try to measure it, it does end up in a specific place, but before you do that, you have no idea. So to try to show you the difference, I have this really cool website I use called The Sky Live, and this gives us a 3D model of the solar system. So I fast forwarded to the year 2059 because I wanted to know when Halley's Comet is coming back. If I click this, 1 second equals 4 months. So again, we can, let's actually slow that down. Let's slow it way down. Okay, cool. So we know where the planets will be. We know where Halley's Comet will be. It kind of went past us, but that's okay. We can calculate where these things will be because these large objects, everything that's larger than just like individual little atoms and molecules, behaves according to Newtonian physics, where we can figure out exactly where they will be and where they will be in relation to one another. So if I want to know where's Saturn going to be on the 3rd of September in 2061, that's exactly where it will be in relation to Earth. But like I've said, in quantum mechanics, it doesn't work that way. So here's how this was discovered experimentally. We know that electrons have mass, and they are a particle, but we don't know how big they are, and they behave in very strange ways. So if you were going to take any type of solid particle made of matter, and a subatomic particle like an electron it fits in with matter. If you were to fire it through a narrow slit, and then detect where they end up on the other side, well, this is exactly what you would come up with. It's a single discrete object, and in this example, some of them, they miss. You don't hit the target, so they end up on the first barrier or whatever. But then some of them, they end up on the other side, but they end up in a really predictable location. None of them end up on the far left or the far right, because how could they? That's impossible. Now, if we fired individual paintballs through, and there were 2 slots, well, then on the other side, they would either line up in one place on the left or on the right, because of course they would. There's literally nothing else. There are no other possibilities. Now, this is how matter interacts. With waves, though, with energy, it's different. So if we were making waves, if we were using like a pebble in this case to make waves in the water, if there's only one opening, one place where the wave can travel through, then the energy of the wave is concentrated in one location. So that's why it says maximum intensity. When you have 2 slits, though, something interesting happens. You get what's called an interference pattern. So because the wave travels through both of those openings at the same time, and waves can do that because a wave is not confined to one location, waves radiate outward in all directions. The waves do what's called constructive and destructive interference. And so that creates this interference pattern on the other side where you get high detection in some locations and virtually no detection in other locations. This is a clip from a Veritasium video and shows it really well. So he's making waves in the water with 2 like little inflated balls. And basically what happens is when 2 crests from 2 waves meet, they amplify each other. But when a crest from one wave and a trough of another wave meet, they totally cancel out. It's like 1 + 1 = 2, but 1 + -1 = 0. So you can see there are bands in here where you see absolutely nothing at all. So, who cares? Well, what ended up happening was this happens with light and it happens with electrons. If you fire electrons, I know it says paintball, but pretend it's an electron. If you fire electrons, even one at a time, through a slot, on the other side, it ends up as just one band or you get detection of them concentrated in one spot. That makes total sense. Electrons are singular things. They have mass, and so they should behave exactly that way. But when you fire electrons, even when you fire the electrons one at a time through 2 slots, this is what you end up getting. They create an interference pattern. So here we can see an example of that. This means that the electrons are waves, or they behave exactly like waves do. So scientists, knowing this, they were extremely and rightly confused. They said, well, that just simply isn't possible. So what they did was they modified the experiment. So instead of just detecting the electrons where they end up on the other side, instead they put the detectors right next to the openings, the slits. And then they're going to see, okay, this is only possible if the electron goes through both slits at the same time. But that just can't be. So let's put detectors in front of each slit or next to each slit, and then we'll see, does the electron go here or does it go there? And it got even more messed up because when they added the detectors, this is what they got. All of a sudden, when you try to see where did the electron go, it ends up behaving exactly like matter. So the very act of looking, trying to detect the electron, interferes with it, and the electron no longer behaves like a wave, it behaves exactly like a particle. So this is why we say you can't know. In this demonstration of the experiment, they're not detecting where the electron is, they're only detecting where the electron ends up. So this is telling us what are the statistical odds, what's the probability that the electron ends up somewhere. And we get the wave pattern because that's how waves are. They just create this sort of pattern. When you try to look, then it no longer behaves that way. Really bizarre. So this leads us to what's called the Heisenberg uncertainty principle, which just tells us that you cannot know a particle like an electron or a photon. You can't know their velocity and their position at the same time. When you detect that electron, like I said before, you don't know where it's going to be next. So that's why we talk about these orbitals as being like three-dimensional structures, and the electron is everywhere all at once. The part of this that we kind of do understand is that in order to observe an electron, it has to be struck by a photon, by some other kind of particle, because that's the only way to interact with matter. But that photon ends up interfering with the electron, and it moves it. It interferes with it. It's like when you're playing pool. When the pool ball when the cue ball hits the other pool balls, they move. They get changed by that. So every single time we observe an electron, we change its velocity. And so there's no way of knowing where it's going to end up next time. I've sort of laid this out already, but it turns out that electrons, they don't orbit around the nucleus in perfectly circular paths either. So while with quantum mechanics we can't know exactly where the electron is, we can know, statistically speaking, where it can be and where it cannot be. So like, think of emperor penguins. I know that there are no emperor penguins in Australia, unless they're in a zoo. In the wild, they only live in Antarctica, but I don't know exactly where they are. Now, theoretically speaking, I could go there and see them, and with electrons, it doesn't work that way. But whatever. The region within the energy level where you're going to find those electrons, that's called an atomic orbital. And an orbital can only have 2 electrons in it. And it turns out that every energy level can have multiple of these orbitals in it at the same time. So these are the energy levels. There's 1s and then 2s, 2p, 3s, 3p, yada, yada, yada. The periodic table is actually structured and organized in this way. So if we just want to pick any random, and you read a periodic table from left to right, top to bottom, left to right. If we pick some random element, like that one right there, I think that's the 28th element, and I think it's copper off the top of my head. It'll have 28 electrons. So where do those electrons go? Well, if we just use these dots, this is where they go. Only 2 at a time can fit in each energy level, and they fill in from bottom to top, which is to say from the least amount of energy to the most towards the top. So this is what the s orbital looks like, and there's a 1s, a 2s, there are 7 s orbitals, but they each look like this. The first one is the closest to the nucleus, the second one is further out, third one's further out, fourth, fifth, sixth, seventh. But they all look like this. So where the electron might be is this like perfectly spherical area, and it's a probability thing. So we don't know exactly where it is. It's just that It's somewhere within a perfectly spherical area around the nucleus. The p orbitals kind of look like dumbbells, and they're each orientated in a different way, an XYZ axis. The d orbitals, there are 5 of them, and they look really crazy. There's like a donut dumbbell one, and then the other ones are kind of look like balloons tied together, I guess. And then these are the f orbitals, and they look even weirder still. So we're not gonna have to like memorize these or anything, but for the record, that's what they look like. So that does it with the electrons. Are you confused yet? Yeah, me too. Don't worry. It's very strange. The smartest people in the world haven't really figured out all of the details behind this yet either. We just kind of have to know the very basics. How electrons behave differently from everything else, where you find them, what energy levels are, what they mean, and all that good stuff. As long as you just understand that part of it, then you've understood everything you need to. I'll see you next time.